Hi all, welcome to part 5 combination circuits. In part 4 what we seen is the design of the adder circuit, right? Particularly half adder and full adder. And that time I given you so just finish that part 4 and come to this part 5. Okay, so then only this one you can follow. And homework like you have to see how that full adder and half adder circuit can be realized in a different way. I mean, full adder expression particularly, how we saw the straightforward minimal SOP using K-map, that one we saw for the sum and the carry output. Now I ask you to find out a different expression using XOR gate using the normal Boolean algebraic minimization techniques, right? So in that way, can you try implementing the full ladder using half hour? So that was a task I given. So this just continuation. I am not explaining what is full ladder right now. So please watch part 4 and come to part 5. So that is the prerequisite, right? So this is a continuation. So we saw that the sum expression of full ladder is something like this. You here you can't do any kind of grouping, and accordingly you struggle, like you are getting a very bigger expression because that K map is not going to help you. Similarly here carry is something like this. So I am trying to show you a different expression for the sum as well as the carry, and accordingly let's see a very nice concept like how this full adder can be implemented using half adder. So let's see that. So what I was trying to do is I just want to rearrange it. I can do it in a number of ways. So here what I'm doing is this x bar y bar z, and the next term of z I'm grouping together plus x y z. The first and the last term I taken together. Okay, so this one and this one. Now the middle two I'm writing now, that is x bar y z bar plus x y bar z bar. Okay, fine, you can do it in different ways, but I just want to in my mind that full adder implementation using half adder is this. That is why I'm doing it in a particular way. So you can do it in different ways also. You can, I think you already tried in yourself, right? So now what I'm doing is this z I'm taking outside, so that this is like a x bar y bar plus xy into z. So by distributivity, by applying like this, you can take this z out, right? Similarly x bar y plus xy bar, you can take that z bar outside. Now tell me, what is this expression? This is hope you remember, this is the x nor, right? The negation of x or, it's going to give you a 1 when inputs are same. Like in both inputs are 0, both inputs are 1s, that is where it is going to give you 1. When inputs are same, the XNOR gate is giving you a 1. So XNOR gate is nothing but the negation of XOR gate, something like this. Or you can write it, there is a different notation for XNOR gate, something like this. So that also fine, but I am denoting it like a negation of XOR because I have a purpose out of it. So this is this one, and here I have Z plus, what is this? This is XOR. I hope it is clear for everyone, right? This is Z bar. Now tell me, what is this one? I can observe it like this whole thing. Let me denote by A and let it be B, right? So here this X or Y I am denoting by A, so that this is A bar B plus here that A B bar, something like that, right? A bar B plus A B bar. Now tell me, what is this A bar B plus A B bar? This is A XOR B, right? So the whole thing is actually the first one XOR the second one. Is it clear? The first one, it's a bigger expression. Let it be this X XOR Y. Let me denote by capital A, and Z I am denoting by capital B. So that this is A bar B, right? And here I am getting A B bar. So that A bar B plus A B bar A XOR B. So the whole thing is actually the first one XOR second one, right? So I am deleting all those things. And let's see what is this. So this one corresponds to what? The first one, that is X XOR Y XOR the second one, that's all. So the whole thing is now a very small beautiful expression you are getting, right? X XOR Y XOR Z. So let me, so this thing is a group, this is another one, and you know this XOR gate whether is associative or not, I given you something in the assignment. You can verify this. I think I already given you assignment for you, maybe in the second module. So I hope you all tried it yourself, or at least right now you know that this XOR gate is associative. So you can do it in any order. If somebody is having doubt, that you can verify, say using truth table method or some other ways. Okay, that you can try yourself. So right now I'm telling you that XOR is associative, so that you can do it in any order. But anyways, this is the way I got. Okay, so I'm happy with that. Now there is something different I'm doing with this carry. Anyways, for carry I got a very minimal expression, but still my intention is like I want to implement this using half order array. So for that purpose I'm trying to implement this carry in a slightly different way. So let's see that. So what I'm going to do is, so this is my carry input, right? Yeah, let's take this color. So just look at this one. So what I'm doing is this y z I'm keeping as it is. So this is my y z term, right? So in K-map, always we will do the largest grouping, right? So that you will get something like this. But I'm doing it in a slightly different way. So this grouping I am having. So what is this? This is x, y. This is, so what I need is actually, I need that y z grouping. So not this one. I'm just retaining this grouping as it is. Okay. So this is your y z, right? So yeah. This one I'm retaining as it is. Fine. But the other two ones I'm not grouping, and simply I'm grouping them independently, right? I can make a bigger group, but I'm not doing that. Okay, but still you will get an expression for it, but it may not be minimal. I'm okay with that. I have a purpose why I'm doing it. I have a purpose. We will see that soon. So if I'm writing like that, this y is that I'm retaining, but for this one, can you tell me what is the expression? This is for this one, the expression is like x y bar is it, y bar is it. Yeah, similarly this one also I am treating independently, so that the expression for this will be, this is y z, and here this one, the expression will be x y z bar, right? So accordingly I can write this c as, what I done is x y bar z first term, and the last term, that is x y z bar, sorry guys, I just made a mistake. It's not like mistake the way I am grouping. This is one grouping, fine, this is also valid only. See, if I'm doing like that, here I will get y z, but something I have a different intention, right? So this is not going to meet my intention, so I'm just removing this at this point. Okay, you can do in a number of ways, but anyways, what I'm trying to do is having some significance. Okay, so finally you will understand why I done like that. If I'm doing in a different way, I will get accordingly, I will get a different one. So here these two things are grouped. Okay, fine. Anyways, that also associativity is there. You can do in a different ways also. So what I need actually is, I need this x y. I want to retain this x y. Okay, so if I want to retain this x y, what I have to do? This is the first one, I think. Yeah, this one I have to retain, right? So so that, yeah, this I want to retain, and I'm independently grouping this one and this one. You can do in the other way also, but if I'm doing like this, I have a purpose for it. We will see that, then only you will understand. So anyways, this is the way I'm grouping. So just erase what happened before from your brain. Okay, so that this term will be, so is it clear now? This is x, right? X, and here this z vanishes and y remains. So now tell me, what is this? This will be like x y bar z, y bar z, yeah, x y bar z, and this will be like x bar y is it, fine. So accordingly I can write this c. So this is there, right? So this c I can write like a x y bar is it, the first term, plus x bar y is it, plus this xy, that term I am grouping because I want to express it using xors. That is why I am doing like this. And this is something now x y bar plus x bar y, so this is xor, right? And I'm taking this z outside and xy like this, so that this will be x or y. So this term I'm getting, right? So now I can reuse it like that. I have many benefits, right? So this into z plus xy. So this is my carry. Now altogether what I was trying to say, let's see. So this is a final conclusion. So now what I'm going to do is, I'm trying to implement the full order using half order. So what I will do is, first I will take a single half order. Let's see. So this is the first half order I am having, half order 1. And for this half order I am applying the first two bits, that is xy and Z is a carry, right? So the actual inputs X and Y I'm applying. And for this half order one, you know the output of half order, hope you remember again, hope you completed the previous part, then only you will understand what is the sum output of half order one. Half order, it is X or Y, right? So this is a sum, so this sum is equal to X or Y, and I'm getting a carry, and the carry is actually X dot Y. Hope you remember this. Now what I'm doing is this one I am applying to a second half order. So this is my half order 2, right? This I am applying to a second half order, and this half order 2 is one of the input is this X or Y, and the other input of this half order 2 is actually that is it. I mean the third input of your actual full adder, right? So all together, now tell me what is this output? This output of the half adder. This is actually the half adder is going to give you XOR of the inputs, right? So here you are getting what? Here you are getting what? That's interesting, right? X XOR Y XOR Z. The first input XOR Y is the first input, and the second input is Z. So this one, right? So you got the sum output of the what called full adder. So that you got. Now how can you get the carry output? So for getting the carry output, what I'm doing is this output I am taking, right, and this one also I am taking. I'm drawing like this is not a good drawing, but still maybe you can try in a different way. So vertically you can draw, okay, fine. So same color let's use. This one I am taking, and this output also I am taking, and both of them I am applying to a OR gate, just an OR gate, a single OR gate, right? And this OR gate is going to give me OR of these two. I mean, can you tell me what is coming out here? Here, the carry output of the half adder is the product of the inputs. Sum out is the XOR of the inputs, right? So product of the input means X XOR Y into Z is what I am getting here, and here I am getting XY. So all together here I am getting X XOR Y into Z, one of the input, or XY, the other input. So that is nothing but this one, right? So the carry out of full adder I am getting. Here I am getting the sum of full adder sums, full adder carry. So that is something extra writing, right? Is it clear? Right, that's all. So what is the conclusion? The conclusion is what? Full adder can be implemented. It's a very nice concept. Implemented using two half adders and an OR gate, right? So this is a very important observation you can have. And also they can ask you in the university exam, like implement a full adder using half adder. So this is the implementation, and this is a detailed implementation that I taken from the textbook. So here I written like half adder 1 and half adder 2. Here that internal circuit of half adder is shown. So this is your half adder 1 and this is your half adder 2, and here you are having the OR gate. And hope it is clear. For the first half adder, the sum output is XOR of the inputs. So that is nothing but using an XOR gate. Inside the half adder we have this XOR gate and AND gate, right? And the second half adder, you are getting the sum output. So this is the sum of full adder, right? Similarly, this is the carry of full adder. So that you are getting. So this is the implementation of full adder using half adder. Two half adder I am using and an OR gate I am using. With that I can nicely implement the full adder. Hope the realization is clear. And using gates, normal and or realization also you are having. That we already seen in the previous part, right? Yeah. Thanks for watching. With this, let's move on to the next part. Yeah.